For years, the strange and spooky world of quantum mechanics has been a realm of delicate proofs and fragile states, often demonstrated in pristine isolation. Scientists have famously entangled photons, electrons, and even entire atoms, but these interactions typically involve the particles' external properties, like their spin or momentum. Now, in a laboratory breakthrough that pushes the boundaries of our control over the quantum realm, researchers have announced the first direct observation of quantum entanglement between the very hearts of two atoms. This achievement moves beyond the particles' outer shells to link their internal nuclei. Imagine an atom not just as a speck, but as a tiny solar system. The electrons whirl around the outskirts like planets, while the nucleus sits at the center, a dense sun. While previous experiments have entangled the planetary orbits, this new work has successfully entangled the two central suns. The researchers accomplished this by precisely using the electrons as a quantum intermediary. They first excited the electrons of two positively charged ytterbium atoms, held perfectly still by laser beams in a vacuum chamber. As these excited electrons danced around their nuclei, their paths created a magnetic field that subtly influenced the spin of the atom's own nuclei. By meticulously controlling this process and then measuring the state of the electrons, the scientists were able to infer that the nuclei of the two atoms, separated by a distance, had become inextricably linked. This is the phenomenon Einstein famously called spooky action at a distance, the instantaneous connection between two particles where a measurement performed on one seems to irrevocably affect the other, regardless of the space between them. The significance of this discovery lies in the remarkable stability of atomic nuclei. Compared to the volatile electrons that are easily disturbed by stray electric fields from the environment, the nuclei are deeply shielded within the atom. This makes them exceptionally quiet and stable quantum systems. Entangling these nuclear hearts creates a quantum link that is far more robust and long-lived than those achieved with electrons alone. It is like moving from a conversation shouted across a windy street to one held in a soundproofed room. The message is clearer and far less likely to be lost to interference. This newfound robustness is a critical step forward for the field of quantum information science. The fragile nature of quantum states has been a major obstacle in building practical quantum computers and absolutely secure quantum communication networks. A quantum bit, or qubit, based on a stable atomic nucleus could maintain its delicate state for much longer, allowing for more complex calculations and the transmission of quantum information over greater distances. This breakthrough opens a pathway toward quantum memories that can store information for extended periods, a fundamental component for a future quantum internet. By harnessing the quiet heart of the atom, scientists are now closer than ever to taming the spookiness of quantum mechanics and turning it into a powerful, practical technology.